So we are live. Hello everyone. Today we have with us Charles Frye. He's a deep learning educator at Weights and Biases. Also done a PhD at UC Berkeley, and he'll be talking about ML research for ML in production. He'll be giving more of his introduction. Hope you enjoy that. So over to you, Charles.
Wonderful. Yeah. Thanks for having me, Yoram. And hello, everyone. I'm joining you from California on the other side of the Pacific Ocean. So it's quite late where I am at. And I'm actually just going to drop into the chat the link to my slides that's in the bottom right hand corner there. Hopefully, folks can see that on YouTube. And I'll be monitoring that chat. So if you've got any questions, please don't be afraid to ask them. All right, and I'm going to dive in because I've got a pretty thick and juicy talk for our next half hour. So the title of the talk is ML Research for ML in Production. As Yoram said, I've worked in ML research at Berkeley, where I studied neural network optimization and applied some neural networks to neuroscience. And then from there, I moved on and worked on applications of machine learning and deep learning. So at Caption Health, working on deep learning systems for ultrasound for medical devices. And then at Weights Biases, most recently for working not in applications of machine learning, but in tools around machine learning. So developer tools for machine learning. So I sort of moved from research into applications and developer tooling. And this kind of like tooling and infrastructure for machine learning ends up sort of straddling between both research and applications. So I've got this this diagram here comes from this course by Simone Scartapane. There's a link there in the slides on reproducible deep learning. So it's oriented at both reproducible deep learning research, so being able to do a deep learning experiment and then be able to reproduce those results 6 months later, or hand off your models to and your code to people who want to reproduce your work, extend your work in a research context, and then also in industrial applications when you actually want to do something out there in the real world with these machine learning tools. So it's a great course, and I highly recommend it, whether you're interested in research or interested in industry. But this concept of ML tooling kind of crosses this boundary, and it's where I've been working for the last couple years. And this has given me a new perspective on research and what is sort of the most important things that I think that academic researchers can be working on to help this broad world of people doing machine learning in production. So that's the goal. I want to sort of give some provocative ideas about what I think academic researchers can contribute to help ML practitioners. And one thing that has made this a lot more interesting than it was maybe 10 years ago when I was first getting started in machine learning is that academics aren't the only researchers anymore. So this is from a paper that just came out of Anthropic AI in the last week here, which shows that over the last 10 years, especially, so between 2010 to 2020, large-scale AI results are no longer coming out of academia. They're coming out of industrial research labs. And this has happened at the same time as the amount of compute required for a big AI project has increased exponentially. So I think that's 12 orders of magnitude in 10 years. And so academics now they're sort of have competition from industrial researchers. So there's people who are doing research work who are not associated with a university, not funded by grants, by governments, by nonprofits, but by private companies. And so this has sort of very much changed the game and has raised kind of the question of what is academic research even for if there are all these private interests, these private companies that are willing to do that kind of work. And I think the answer of why we need academic research is that this kind of publicly funded, publicly oriented academic research exists to perform all the socially necessary intellectual labor that private interests are not well incentivized to perform. So the like canonical example of this is the sort of like high risk long term technology development, right? The idea is that for everybody in the world, our long run increases in prosperity and like wealth and comfort come from technological improvements, but investors, private actors seeking returns, they really just care about their own personal prosperity, which is not always very well aligned with these sort of long-term goals. And so, we can build these transformative technologies in academic labs. When they're publicly funded, they often become sort of public goods, like the internet, or all the unpatented technology like deep learning that has come out of academic research. So that's one way that academic research can do something that private interests aren't necessarily going to do. And this kind of like high risk research and development is a staple of machine learning, right? It's maybe hard to believe now, but at one point, deep learning was a crazy idea that just like 10 people in the world cared about and worked on. And like all of them were in Jeff Hinton's lab or in Andrew Ng's lab. So this was high risk in that it was not clear at all that deep learning was going to be successful. There's a lot, the world of machine learning is littered with cool ideas that didn't quite pan out. Um, Nowadays, I mean, obviously, deep learning is no longer high risk, but there's like high risk research still going on. Alternatives to backprop, the algorithm that we normally use to compute our gradients and train our networks. Alternatives to gradient based learning, so different ways of doing machine learning that don't involve taking gradients of loss functions. Like evolutionary learning, there's still lots and lots of high risk R&D to do in deep learning, including like really hard applications of deep learning. Like it's still really hard to make a robot that can act on its own with deep learning. It's really hard to handle long-term memory and decision making over long periods of time with deep learning. But those kinds of high risk, long term kind of research programs are increasingly being done by industry researchers and engineers. So, for example, there's no obvious immediate short term benefit really to beating a world class Go player at Go, but Google through DeepMind created the AlphaGo network that ended up beating Lisa Dole a couple years ago, and uh, there's even more recently, actually, maybe a better example, AlphaFold was a solution to the protein folding problem, a really like long-term challenge in biology. Took a ton of effort on the part of DeepMind, but like ended up cracking a really difficult problem. So that's another sort of like high risk, high reward research direction. And then there's also lots of stuff going on. These are all actually from DeepMind here. I just to emphasize how much of this work is going on, I'm just talking about one of the like top 5 places where this stuff happens. They also work on a lot of stuff that's sort of like pushing the envelope on like weird ideas directly in deep learning. This decoupled neural interfaces is kind of like a way to speed up gradient descent and gradient calculation. So all this stuff is being done, and that decoupled neural interfaces paper, great paper, not the sort of thing you would normally expect to come out of industrial research. So, like, given that all that stuff is being done in these industrial labs, I guess maybe the response is like maybe you should just do what they're doing. So if you can't beat them, just join them. And so there's lots of sort of open research groups forming now. The ML Collective, Hugging Faces research groups, Aloyther AI. I think Yaron mentioned that he follows the work that they do there. These are these sort of more open groups that allow people to sort of like join in, pull their resources together, and even if they aren't working at Google or at some big fancy company, they can work on artificial intelligence research and do some of these this like fundamental tech development, like working on AlphaGo and AlphaFold, but in this open setting. So it's totally an option. Another option, and this is again from that Anthropic AI paper that just came out this week, is the academics are kind of falling behind the private sector because they don't have as many resources. So computer science research has traditionally been really cheap because computers aren't that expensive compared to particle accelerators or MRI machines. So computer science departments don't have giant grants. But that could change, and so the academics could push for their granting agencies to sort of create the experimental infrastructure that they need to create large supercomputing clusters oriented towards deep learning to make, as they call it, the financial and structural investments necessary to allow that to happen and done sort of like publicly, maybe at a national or international level. And as they point out, this is really important because the academic and public sector motivations stem maybe more from the pursuit of knowledge rather than profit. And it would be sort of like a different set of a different kind of work would be done at that scale. Um, so sort of trying to do mostly similar things at a big scale is definitely one solution here. And then, of course, you also this is maybe the purists. If you can't beat them, join them. But you can also you maybe you're not that interested in like long term academic research. You just want to get a job at one of these places doing that kind of industrial research. So when you're going into your internships, to your master's program, your PhD, whatever, you could just pick a topic that they're interested in, try and get a paper into something like NeurIPS, ICLR, these conferences that they pay attention to, get yourself noticed by them, and now you can do an internship at FAIR, working with the folks at PyTorch or with Jan LeCun, and then graduate and move on from that phase of your life and become an industry researcher or engineer. Uh, totally acceptable option. But what if you really are interested in this pure academic route? Um, Actually, you could try and do things that are different from what those labs are doing, but are interesting to them. So, like, if you really, I guess, before I talk about a bunch of ideas that I think you could pursue, if you really want to like break the mold of what's interesting for those kinds of industry groups and do a different class of academic work. I think maybe some people seeing a title like Research for ML in Production maybe really want to follow this path and get on the track to becoming an industry researcher or engineer. So if that's you, I do have some suggestions for you, and they have a similar theme: bitter lessons and scaling laws. So a lot of academic research is done with like architectural fiddling, like try out a different type of convolutional layer or like new style of data augmentation. And the goal is to get state of the art on benchmarks, do a bunch of hyperparameter tuning, or maybe come up with some really clever, complicated algorithm to solve some specific problem. And a lot of good stuff has come out of that kind of work, but it's a tremendous focus of the field, and there's not as much yield there. There's certainly fewer low hanging fruits, and even the fruits that are low hanging have turned out to be rotten often. So these approaches that work at a small scale often fail to scale up to the scale that we need when we're building the like contemporary deep learning systems. So Richard Sutton is one of the main workers in reinforcement learning going back 50 years. And he recently, just in the last 2 years, wrote this essay called The Bitter Lesson that said the biggest lesson that can be read from 70 years of AI research is that just trying to use as much compute as possible is ultimately like the most effective approach to solving a problem, because compute just keeps getting cheaper and cheaper and cheaper. And so human ingenuity of coming up with cool architectures or clever algorithms tends to lose out to just trying to work at the biggest scale that you can and like push the envelope there. So because of that, it can be really hard, to work except at that scale to like really push things forward. Um, and the uh, but there is a way around this that has just come out of work at OpenAI in the last couple of years, which are these neural scaling laws. So 3 neural scaling laws appear here in these three figures here, that show that as you increase the amount of compute power, the amount of time that you spend training a model, the test loss will goes down following a very simple mathematical equation. So the best performance on the test set is very predictable from the total amount of computation power that you put in, holding certain other things fixed. Similarly, as the amount of data that you feed it goes in, there's another scaling law that predicts that very well, for this particular natural language problem. So this was work before, while they were working on GPT-3, planning the training of GPT-3. And similarly, as you increase the amount of parameters and hold other things constant or scale them appropriately, you have a simple scaling law as well, these power laws. And what this allows you to do is, if train it running enough compute to say, this one is 10 to the 1 petaflop days. So 10 petaflop days is, we're on the order of hundreds of thousands of dollars just to get a single data point down here. That's the scale at which experiments like GPT-3 or these big contemporary models work at. That's really expensive. But because there's this simple law, you can do a bunch of experiments down at this smaller size and then use that to sort of predict what your performance is going to be at a bigger size. And so if you want to influence industry labs and sort of show industry labs that your ideas are good and will work for them when they work at their scale, at the internet scale that they operate at, working on these sort of scaling law analyses of the work that you're doing is probably the way to do it. So look at your architectural changes, not just with one training run at a particular data set size, particular amount of training, yada yada, but at a bunch of different sizes, from maybe even super super small up to maybe up to the normal size that people work at, which is enough to fill a whole GPU. Oh yeah, a comment from Bovnik, a recent work called Scaling Laws Under a Microscope, which is even better to predict scaling laws for different NLP tasks. Nice. Yeah. So there's work happening on scaling laws. There's a bunch of things out there about, there's a really long appendix to the neural scaling law paper. There's lots of detail about getting this right. So it's not something that's super easy and straightforward, but if you do it with the work that you're doing, it'll be a lot easier to sort of make the case that your research is actually important for these for these big industrial labs that are building large language models, large pre-trained computer vision models, all this kind of stuff. So I would recommend diving deep on that if that's something you're interested in. But there are actually lots of other public goods that academics can create. Going back to this idea that the goal of publicly funded research is to create these public goods that wouldn't happen if all research was just done at private companies that are motivated by profit. So open source software is an obvious one. Open data sets, open standards and agreements on data formats or particular problems to approach or benchmarks. And then also just education and socialization, sharing these ideas, teaching people how to use these ideas. These are all public goods that academics can create. So the framework that I have for coming up with good ideas for research for ML in production is start off by considering what the deep learning in production world needs. Obviously, they'd love fundamental technological advancements. They'd love for people, to do cutting edge applications of deep learning that they, can bring into their startups. But try and filter to where academic research can best help, because it's sort of least likely to be done by one of these industrial labs. So these fundamental technological advancements, there's a lot of people already working on these on those kinds of problems, and including at industrial labs. And cutting edge applications are very monetizable, so they're likely to happen at startups or at big labs. So let's look at some of these other options. We will quickly go through one more like concrete research idea that isn't a bad idea to work on in academia, but it is the kind of problem that's likely to be done in industry. So one of the big differences between what happens in deep learning and machine learning research at universities and the kinds of data sets that people care about in industry is in industry data is generally tabular. It's in tables, so it looks a little bit more like an Excel spreadsheet than it does like an HD movie or like an image or audio. So lots of companies have these big databases of user information or sensor information that they're collecting. Maybe I'm a power company and I'm collecting I have a database that just sucks up all this information about the state of all the power lines and how much power is being consumed by different areas, what's coming out, how much power is being generated at different uh, power plants. So it's a very different type of data, and in general, deep learning doesn't work super well on tabular data. So there's been some work in the last 2 years trying to do deep learning for tabular data with transformers, with graph neural networks, with other types of things. And in general, deep learning, like these approaches, haven't done super well. So I've got two little posts there. One, sort of post critiquing some recent work on transformers for tabular data, and another more thorough research paper from some folks at Intel. Also doing a pretty thorough takedown of recent deep learning approaches to tabular data. So this is important problem that is really important in industry, but it's also something where they have all the data that they need, and they really care quite a bit about solving this problem. And so it's probably not a great place to spend your work in your internship or your dissertation, because it's likely somebody from Google or Facebook is going to publish this. Publish their new result on this, at the same time as you're working on it. So just looking back here at this page, what are some of the things that where academic research can do stuff that maybe wouldn't happen at these kinds of industrial labs? So publicly releasing data sets, doing sort of like careful experiments and broad theories around data drift and data sets that change over time, creating engineering guarantees and doing rigorous analyses of failure modes in ML systems, creating sort of standardized pre-trained models that can be shared by everybody that are also like publicly available and free. And maybe a little bit more speculatively, creating a professional code of ethics for ML. So these are things that I think that the ML in production world really needs. They're not likely to do it themselves, and academic researchers could do. So I'm going to dive in detail on each one of those ideas now. So first, creating standardized, free, public pre-trained models. So the analogy that I want to go through here is like back in the 80s when people were first working on like like the sort of like mainframe generation of useful computers. Everybody had to write their own floating point arithmetic. So if you've used floating point numbers, if you've looked closely at floating point numbers, you know that it's actually really, really complicated. What happens when you do 1 divided by 3 plus 1 divided by 3 in a computer is a lot more complicated than what happens when you do it by hand. And IEEE, this international engineering consortium, came up with just like one specification for here's how you should do this. Here's how to handle all the edge cases so that people could write algorithms on one machine and then run them on another and not have to worry about numbers behaving super differently from one to the other. And right now, with things like neural network embeddings of images, if I'm using BERT to embed my sentences versus Distilbert versus Elmo versus some GPT type model. I'm going to get something completely different. So imagine if instead of having all these like sort of private companies creating these individual models for individual tasks, if we had a sort of like IEEE image embedding data type, like an IEEE floating point data type, that would be more portable across systems, and that people could do a lot more engineering around, like specialized chips, maybe for example. Um, and there's some caveats to this as a research idea. One, people still want the like latest and greatest thing in their embeddings, and that outweighs a lot of the broader engineering concerns about like portability, reusability, stability over time. So while people still want to edge out a little bit more performance, maybe it's too early to decide what an image embedding or a sentence embedding looks like. And then also floating point numbers are already really complicated. Maybe it's too much of a pipe dream to imagine that we could standardize something like image embeddings. Um, but like despite those complications, it's already the case that like startups are working on embeddings as a service. So OpenAI is maybe not a startup so much anymore, but they're offering you give them text and they put it through GPT-3 and send you back embeddings. There are like competitors in that space. So this is already kind of happening in a private space. And if you can imagine how bad it would be if everybody had to pay like 10 cents every time they multiplied two floating point numbers to whoever came up with the floating point spec back in the 80s, because it was done by a public body. That's something that that's part of our shared heritage of humanity now. It'd be great if image embeddings and text embeddings were the same way, and that's the kind of thing that academic groups are really well poised to do, but that these private actors are unlikely to do. Similarly, releasing high quality data sets is something that has driven ML forward in the past, but that private companies are less and less likely to do. So a lot of ML research has been driven by open data. So one of the early successes of deep learning was LeNet, Jan LeCun's network for digit recognition. That was powered by the MNIST data set of handwritten digits. The original data set, the NIST in MNIST, stands for the National Institute of Standards and Technology. They're the ones who originally collected the data, got people together, had them, had them write on pieces of paper, took the pictures, centered them, like created the data format, all that kind of stuff. So that was done by a public body. AlexNet was another big like step forward in deep learning in the early 2010s. AlexNet was trained on the ImageNet data set. And the ImageNet data set was collected by professors at Stanford, Princeton, and UNC Chapel Hill. So all grant funded people. Then a lot more recent, even more recently, GPT-3 trained at OpenAI. That was based on the Common Crawl data set. The Common Crawl data set is like a large fraction of the internet, basically. And the Common Crawl is collected by a nonprofit organization. And so these are some of the biggest advancements in machine learning and in deep learning in particular. These three architectures, and they were all based on open data created by like nonprofit organizations. And one reason nowadays, like it's now clear that this is super important for the advancement of technology, but that technological advancement, a lot of private actors would rather that happen just for them. They would rather collect the data and then be able to use it as their secret sauce for training their deep learning networks, their machine learning solutions. And so there's this tragedy of the anti-commons, which is the opposite of the tragedy of the commons. The tragedy of the commons is when there's a public good and then people use it all up. Selfish individuals use it all up. A tragedy of the anti-commons is when selfish individuals fail to create a public good. So because data is a competitive advantage, private actors are disincentivized to share it. So that means it's something that like this is a place where academics can step in and help out both their fellow academics and the world at large. Um, uh, but it's easier said than done to release a high quality data set. For one, scale is super important. You need like a big data set to be useful these days, but that can be expensive. Data needs to have longevity. It needs to stick around. So it's probably not something to work on as a lone graduate student or as part of your own um, like cornerstone project or internship project. It's the sort of thing that like an agency or a consortium of research institutes should work on so that it can stick around for a long time. And then also this sort of like data curation is really detail intensive and kind of thankless. It's not as sort of flashy and exciting as working on algorithms. So that makes it, it takes a lot of gumption to see that one through. And a lot like all the attention to detail required to do hard algorithmic work or hard mathematical work, but with a lot less prestige. So there are people who are doing this kind of work and doing it really well. There's a really great data set for sign language called How to Sign that came out in the last year that does all this stuff about scale, longevity, curation, all very well. So check that one out. If you if you want an example. By the way, I shared the link to these slides in the YouTube chat, and they should be added to the description at the end of the event, so that you can get to the links that are in my slides. Um, so in general, people would really benefit from data sets. I think that's probably not news to anybody. Like Andrew Ng said, data is the new oil. So that's probably not news. One thing that people in industry care about, maybe more than you'd expect if you've only ever been in research, is change in data over time. So data in the real world, where people are applying machine learning algorithms, changes, and this is called data drift. So a really like salient example of this is when the coronavirus pandemic started. Everybody's behavior changed around the world pretty much simultaneously. So there's this cool article on Fortune.com about how Instacart had to just like completely rethink, rehaul its machine learning models because of that sudden change. Like every model was suddenly not working nearly as well anymore. I think they went on one problem they went from 90% accurate to 60% accurate in just like a couple of days. So the like data in the real world is going to change. It's not going to stay fixed. And that's a huge difference between the way ML is done in labs and the way it's done in industries. In labs, we have fixed data sets like MNIST, like Common Crawl to a certain extent, like ImageNet, and then like labs kind of like often compete to maximize their performance on like that benchmark data set. And that is a lot of benefits to have these fixed benchmarks, so you can do really nice apples to apples comparisons between models. But that's a huge, but that's it's sort of fictitious, right? Like there's this fixed data, and it's not changing over time, unlike data in the real world. So having open data sets like ImageNet or like MNIST, but that kind of constantly change and update over time, just like data sets that companies collect and that are like encountered in the real world, would be like very beneficial for making the work done by research groups more translatable, and by helping even also these like industry labs focus more on this like problem of data drift. Um, the one big caveat on this one, though, is that collecting data continuously really increases the complexity and expense of maintaining this data set, because now you have to be like constantly updating it. So this is really not something to do as just a lone graduate student, but really something that like you should get like a department at a university behind, or get like lots of people working together to create a really nice continual learning data set. So uh, one solution that people are aware of this problem of data drift. They know that it's happening in the real world, even though we don't have great academic models for it. And one solution to this is just like regularly retraining on new data. So like not really, or like in the most extreme version, like dropping the split between training models and running inference in models. So like every time something goes through the model, the weights update. Like the model never stops learning. Humans, ideally, never stop learning either. So it'd be great if our models kind of did the same thing. That's at least it seems that the way that humans handle the fact that that data drifts is that we just never stop learning. Uh, so that like that is a nice intuitive appeal, but um, it really breaks a lot of the like mathematical models of machine learning and what little understanding we already have of what's going on when we optimize deep neural networks. Open questions on what can we say about what optimization means in this setting and what happens in a continual learning system over time. Are there architectures out there that might be better for continual learning? You may have heard of catastrophic forgetting, which is that as neural networks train and learn more tasks, they tend to forget other tasks that they have learned. The sort of like weights overwrite for the new task, overwrite what has already been learned. So, what can we do to make our networks handle that better? Um, so there is work happening on continual learning, and some of it is happening at these kinds of industrial labs. I think the kind of like fundamental mathematical work maybe is a better shot for people in academic labs. But sort of like centralizing and coming up with what the problems are in data drift would be in data drift and continual learning would be beneficial. So maybe I think more so than coming up with continual learning theory and continual learning algorithms, maybe what academic groups can do is produce better models and observations of data drift. So slowly, this kind of like typology of different ways data can drift has emerged. There's like sudden transient changes. There's gradual changes. There's seasonal changes. There's changes in just the labels versus changes in other parts of the data. And then there's also like drift that's caused by the fact that models are interacting with the users. Like I know that the videos I watch on YouTube and the music that I listen to are influenced by algorithms that suggest videos and music to me. But I don't think that there's very good like mathematical theory on what is happening there, and how we can design our models so that the outcomes there are beneficial for users, beneficial for the machine learning teams that deploy the models. So like understanding that typology is like super loose and like feels very shoot from the hip. And academics could do a lot to like really firm up that sort of like hierarchy or taxonomy of drifts and understand them better and understand how they impact performance. How does a concept drift versus a label drift show up in data and in the behavior of your models? And how can we measure these things better? It's really difficult to measure a lot of these kinds of data changes, and the so better data sets for observing model drift, and then better methods for measuring these things would um, would be really helpful. So, a question coming in from Bovnik: can we not just pre-train models for less steps, or retrain models for less steps at a regular time, like every quarter or half year, instead of continuous learning? What are the benefits of continuous learning? Yeah. So what you so the proposal is just like retrain the model every couple months. And that is a form of continual learning. I would say there's two things. One, if it takes you $10 million to train your algorithm, then you probably don't want to do it every 3 months. You probably want to like not start from scratch every 3 months. And we don't know that much about what happens when you sort of like warm start a model when it's not starting from random initialization, but from something that's already learned. Do you need to increase the learning rate or decrease the learning rate? Should you randomize some of the weights but not all of them? Should you freeze the earliest weights and only change the later ones? And that's those are all sort of empirical questions and things that people can do research on. I think, but maybe a better answer, Bavnik is sort of suggesting like retraining on like a fixed schedule, as opposed to continuously learning. Like I'm suggesting here with continual learning that you never stop learning. Um, and I think the benefit there is like the coronavirus pandemic happened pretty fast. And the change in behavior happened very fast. It did not happen in 3 months. It happened in like, in where I was in San Francisco, like, one weekend, everything is fine. You can do whatever you want. By Wednesday, we're on lockdown. And so everybody's behavior changed. Um, and so you never know when data drift can happen kind of like instantaneously. It can happen really, really fast. And so the like continual learning solves that problem by always being ready to learn. So that's I think the clearest benefit I can offer. But great question. Thank you. All right. So observations, models, data drift, continual learning. Um, Great. So a bit of a pivot, but one kind of research that I would really like to see in deep learning is something that's actually already been done for a bunch of other computing paradigms. So the paper title I would like to see is "Why Do Deep Learning Systems Fail and What Can Be Done About It?" I think data drift is one of those causes. So the this lineage of papers actually goes back to the 80s, which was the like mainframe terminals and databases era of computing. And the paper was "Why Did Computers Stop and What Can Be Done About It?" And it was all about building fault tolerant systems. But it specifically like collected up all the bug reports basically at this place called Tandem Technologies, and sort of and quantified what were the most common and least common causes of system faults and system failures. And out of that research came some of the like core ideas for database design. So this acid principle of database design came from Jim Gray, the guy who wrote that paper. Then about 20 years later, another paper came out, "Why Do Internet Services Fail and What Can Be Done About It?" That demonstrated that the like some of the most common, and this is 2003, so this is like .com era. So we've moved away from databases and mainframes and over to internet services. Where you're running your own data centers and server farms, and serving requests for America Online or Yahoo or whatever. And so this studied failures in internet services at that time, and identified the most common causes. A big one was just sort of like operator error, like people misconfiguring systems. And so it suggested a bunch of ways to avoid those kinds of issues. Uh, uh, on another 20 years pass, and there was a paper just recently about bugs that caused cloud incidents. So incidents, it was basically like every failure of a large system in Microsoft Azure in 2019. Um, and again, like some of the biggest problems were sort of like configuration of systems were like the most common problems. So all of these papers, like a lot of the ideas in the papers are maybe obvious in hindsight, or maybe people kind of believed them on the basis of their experience. But these papers collected up a ton of examples, and then and quantified a lot of these trends, and then sort of extrapolated from what they could see quantitatively, to give suggestions for how to design better systems in the future. And like we don't yet have a paper like this for deep learning. There are papers out there about machine learning systems that are like that do worry about these engineering problems. But I'd love to see like this kind of paper, and basically it just takes in most of these cases it's sort of like a partnership between some folks who work at a university, and then folks who work at these in industry, to sort of like get the data out of these practical systems and then analyze it with an academic approach. So that's like fruitful ground for collaboration, I guess. Why do you need why are academics even necessary here? If this data is going to be coming from production ML, why does an industry do it? I think the main reason is like the a little bit of The internet services in this one are anonymous. It's sort of like hidden what their names are. And similarly with the production cloud incidents, sort of Microsoft is collecting up all these failures. Nobody really wants to talk about their failures, even though learning from mistakes is so important. And so it's academics can sort of like create a veil of ignorance between the readers and the failures. So on that same theme of designing better systems, one of the things that's really missing from deep learning is engineering guarantees. Deep learning systems can do these like magical things like translate text between languages, find text in images, and drive robots. Um, but just seeing that they work well in a lab or watching them work well for hours at a time doesn't tell you what's going to happen if you scale that up and all of a sudden everybody has it running on their phone at all times. And that's kind of scary because there are deep neural networks in almost every smartphone, and there are deep neural networks running on tons and tons of your data that have been collected by different companies, and nobody really can guarantee that these things will not give horrible outcomes. And just like compare that to airplane design. If I'm going to build an airplane, uh, I have to compute a chance of fault for each component. What's the chance that this component will fault or break? And then take a sort of like systematic approach to quantify the chance that the whole system, the whole airplane, fails because of component faults, and then sort of avoid it by different types of redundancy. So the like fly-by-wire systems that pilots use to autonomously fly planes achieve failure rates of like 1 per 1 billion hours, and this standard is sometimes colloquially called as reliable as the wings. Right? We know a lot about how to build the physical wings of an airplane, and if the fly-by-wire system is going to be as important as the wings, it better be as reliable as the wings. And deep learning systems are not as reliable as the wings, compared to compared to how reliable airplanes are, compared to how reliable the physical components of a computer are. Or if you, I don't know if you've ever taken a database class or learned about databases. There's this incredible amount of redundancy and reliability built into these systems. And we just are not even close in deep learning. And in industry, it kind of feels like they're too busy moving really fast and trying to become state of the art and like create these amazing miraculous demos, and they aren't thinking about these kinds of engineering guarantees. And this is something that requires like very kind of hefty mathematical and engineering work, and that I think that engineering focused research institutes could really be doing more of. So just to give you a sense for what this kind of approach might mean for autonomous vehicles, a lot of people have argued that autonomous vehicles should just be as safe as humans. And if that were the case, then autonomous vehicles did all the driving, then they would kill as many people as humans do with when driving vehicles. So that's like in the U.S., that's like 35,000 people a year. It's 100 people being killed a day by this autonomous system. If we were able to achieve the like as reliable as the wings standard, that's like, well, it's one death a day is actually 5 times that 1 per billion hours um, standard. So that would be one death a week from autonomous vehicles, and that's autonomous vehicles would make the world a better place, even if in some ways, even if they didn't even if they killed people as often as human drivers. But like, shouldn't we be aiming for like actually sort of like transforming and getting rid of this like consistent cause of tens of thousands of deaths, and like solving that kind of problem, and like making these kinds of engineering guarantees is the kind of thing that would really make like deep learning applications like clearly beneficial to humanity. So these eventual standards are going to come out of like interaction between industry, government, and academia. But a lot of the foundational mathematical work that needs to be done on this, like needs to be done in academia, sort of like quantifying these things and maybe even coming up with the kind of like principles that are both like mathematical and rigorous, but also practical. And then there also needs to be like a cultural shift among machine learning engineers. And in academia, we are at the intersection of people being trained to do things and the like world's experts in things, right? There are students and there are professors, and so the like engineering professors can like as they do this work inculcate these values in the next generation of machine learning engineers. Which brings me to my like final big idea here of a topic of a sort of like research topic. Um, Maybe it's hard to call this one a research topic, but I think one sort of like final outcome of making deep learning sort of like more rigorous and more like airplane design would be a professional code of ethics of what is and is not like ethical to do with machine learning and how and even just like sort of how to think about those problems. So the like physical engineering disciplines, like aerospace engineering, civil engineering, electrical engineering, they all have like a really clear sense of their responsibility and their duty. Like they know that the systems that they build can kill people, and they approach it with that level of seriousness. Medicine has this with the Hippocratic Oath going back millennia. Law has this, etc. But software engineering, from which ML engineering is sort of springing, doesn't have the same culture. And this has not worked out super well in the end. Big tech has found itself with a lot more enemies than it had 10 years ago, than it had 20 years ago. And part of that is this like move fast and break things culture that, people actually don't like it when you break stuff. And so machine learning, as it develops itself as a separate discipline from software engineering, has an opportunity to correct that mistake. And this is even more important because machine learning kind of promises to get out there really into people's lives in like a very deep way with you know uh like surveillance systems, with like making really important decisions and removing human decision making in a lot of places. A lot of those are really, really like safety critical places, are really important places in people's lives. And so it's really important not to have a move fast and break things ethical code as a profession. And this code of ethics is probably going to need to come from outside of the industry and not just from the industrial actors, because these industrial entities aren't really credible creators of this code of ethics. They have monetary incentives that push them to choose money over ethics, and it's also because the boards and the leadership come from the world of big tech of the last 20 years, from Silicon Valley venture capital and uh, uh, these people like don't have the credibility for this, but the sort of like engineering academia does have that credibility and doesn't have the same perverse incentives. So this is like highly impactful, very long term, I think, thing to think about. But it's not not the kind of thing that these private research groups are going to work on. In fact, there's been some very prominent firings of ethicists and people interested in these dimensions of machine learning and artificial intelligence from some of the big groups. So that's that's a bit scary, but it's also means there's an opening for good work to be done, and maybe suggests how important that kind of work is. All right. So wrapping up, did I have wrapping up just some of the things that I think that academic research can sort of like best separate itself from industrial research while still being super, super useful. Um like at a very high level, engineering guarantees for ML systems and an engineering professional code would be like incredible. And I'm looking forward to the work that's going to happen on that in the next decade. Maybe a little bit more narrowly, I think there's a lot of work to be done in continual learning and data drift and data sets that change over time. In the tradition of creating high quality public data sets in academic institutions, sort of orienting more towards that will help it be more useful for the next generation of machine learning systems. And then just as there's a history of public data sets, I think there should be in the future a history of pre-trained models, of public pre-trained models that can um, uh, that can deprivatize the process of uh, preparing rich data like images, like text, for processing by downstream systems. These are all places where academic research can really contribute. Um, so I think there's a lot of great work to be done. I'd be remiss if I didn't note that there are some challenges. Um, Number one, this is not the easiest path because there are now and there will be for the foreseeable future more jobs in industry than in academia. So it's definitely the easier thing to optimize for industry employment rather than academic employment. So this is definitely, I think it was Ilya Sutskever at OpenAI who recently tweeted that an academic is somebody who has chosen to forego material comforts for the prestige and honor of their peers, and that's not everybody. So that definitely makes this a challenging path. And even for academics, the incentives aren't perfectly aligned. I was talking sort of about, like in a very idealistic setting that academics create public goods and they receive for that purpose public funding. But in practice, it's incentives come from the people who give out that money and give out that prestige, the tenure boards and the granting agencies, the academic departments and the government departments that control academic careers. So that means that all of these approaches that I've put out here, like a code of ethics or like public data sets, a lot of those things, they're not research citations, which are what tenure boards and granting agencies are used to incentivizing. So finding a way to make sure that creating a sick data set or creating an open source software tool are treated with the same sort of like respect and and count the same for your career as publishing a really prestigious paper. Um, that's something that has to be advocated for by academics to these groups. And that's not yet the culture. It's changing. Open data, in particular, like people are starting to come around to that. But these other sort of like next generation kinds of ideas, still, we still have to convince the um, the money people and the department heads that those are good ideas. So that's all I have for my talk. I would love to take more questions if there are any, or Yoram, if you wanted to ask some questions. But just a note, I'm on Twitter. That's my Twitter handle, Charles_IRL. My DMs are open. That's how I ended up speaking here. Somebody reached out to me. So please feel free if you've got any questions about research or about ML and how to get started. And I've also got my personal website there, charlesfrye.github.io, where I write and blog about machine learning and mathematics. Um,
Yeah, sure. That was a great talk on industry versus academia, and it answers a lot of questions for people who are deciding and seeing. What is it. One personal question I had, you mentioned ethics. So, how different is academic rivalry? Does it promote good research, and what is its counterpart in industry? What is it?
Yeah, so there's definitely, academia is not just a bunch of publicly minded people just doing good things for the world. There's more of it and more public mindedness and good spiritedness, perhaps, than there are in a lot of industries. Um, I would say that um, Yeah, it mostly comes out in terms of like competition for funding. A lot of it happens sort of like behind closed doors, so it's hard to see exactly what is going on. I think the biggest, I guess the most important takeaway probably for somebody beginning a research career is to make sure that you've got your friends, that you have people who are working on these kinds of problems with you. That a lot of the things that I described, like a professional code of ethics or open data sets, like the more people there are who are uh, like on your side and working on this with you, the better you'll be able to like overcome these kinds of like petty rivalries, or be able to get a hold of the resources that you need. So it's I guess if you want to be public minded and oriented to the public good, make sure you've got people on your side.
Yeah, that definitely makes sense. Yes. So yeah, as Bhavnik says, it was a great presentation. It was indeed a great presentation. We learned a lot.
Yep, thanks for having me, Yoram.
So if there's any more questions, if there's no, we can end this broadcast. Right then. So as Charles said, you can reach out to him on Twitter anytime. He has given his ID. So thank you everyone.
Mhm. Take care.